All right, welcome. In just a sec, we'll get started. So we're going to be moving on to chapter 7. And again, we'll get started in just a sec. And if you have any questions, feel free to type them in below. Okay, so we're off to chapter 7. And chapter 7, we're going to talk about gases and talk a little about liquids as well. Not sure how much solids we're going to talk about, but mainly liquids and gases in this sort of chapter. And so in this chapter, there's a lot of gas laws that we're going to talk about. So as we go through, you'll see a number of sort of formulas that are boxed, and obviously we'll go through them. And you are going to need to know the formulas for these different gas laws that we're going to talk about sort of in this chapter. All right, so let's get started then. So we're going to start off with gases and sort of substances that exist as gases under normal conditions. And when we talk about substances that exist as gases under these normal conditions, usually when we talk about sort of normal conditions, we're talking about a pressure of 1 atm. ATM is an atmosphere, as we'll talk about in this chapter here. And that's a very common unit of pressure that we see a lot. So fortunately, no money coming out of that. So it's just an ATM, which is the abbreviation for it. The temperature, typically when we talk about temperature under normal conditions, and again, this is different than standard conditions, which we'll also talk about a little bit later on this chapter, but under normal conditions, that's sort of everyday conditions, sort of conditions that we typically will find values for in tables, sort of in chemistry and stuff like that, is a temperature of 25 degrees Celsius. And at those sort of normal conditions, everyday conditions, ionic compounds typically do not exist as gases under normal conditions. And that's because what really holds them together, as we'll also talk about later on in this third chapter as well, something like ionic compounds is that electrostatic attraction. So that's that attraction between the positive guy, which is our cation, and our anion. So we have our attractive force between our cation, which is positively charged, our anion, which is negatively charged. And that really strong attraction between those two, like we talked about with ionic compounds and doing nomenclature, is a very strong, what's known as an intramolecular force. And under normal conditions, like at 25 degrees Celsius and 1 atmosphere, which is again normal sort of pressure, that doesn't typically happen, that they're able to basically separate from each other and go into the gas phase. So you would need a lot of energy to allow something that's ionic to kind of do that. And it just doesn't typically happen. So when we have ionic compounds, typically what we'll see as under normal conditions is, if you start heating them, for example, they'll more start to melt rather than go into the gas phase. So for example, something like sodium chloride, um, which is salt, NaCl. Under normal conditions, again, it's very hard to sort of get those guys into the gas phase. So, when we heat up something like salt on our fries, for example, which is good, we don't get like toxic chlorine gas coming out of that as it breaks apart or anything like that. So, um, typically ionic compounds, because they're held together by those really strong forces, uh, really don't exist as gases under normal conditions. Now, when we talk about molecular compounds, again, these are guys that are basically going to be sharing electrons, so sort of covalent compounds, covalent bonds sort of happening. They're a little bit different. There are some molecular compounds which are gases under normal conditions, so things like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, CH4, which is methane. These are all sort of gases under normal conditions. Methane, again, being kind of like the gas that comes out when you light a Bunsen burner. But a majority of molecular compounds are also liquids and solids at room temperature. But the major sort of difference between, say, a molecular compound and an ionic compound when we talk about sort of gases is molecular compounds are easier sort of converted into a gas than obviously ionic compounds. And that's because when we talk about, for example, something like water, when we talk about water, basically several water molecules are held together by what is referred to as intermolecular forces, which we'll also talk about again at the end of this chapter. And what happens, for example, when we heat water is this force that holds this entire water molecule here together with this entire water molecule here is not as strong as, say, that intramolecular force that we see in ionic bonding. So as we start to heat it, it will break this bond between the two water molecules, and then you'll have one water molecule that could go into the gas phase, the other water molecule that also go into the gas phase. So it's a lot easier usually in molecular sort of compounds to get them into the gas phase. And that's because essentially what we're breaking is the bond between individual molecules, as opposed to an ionic compound where you essentially have to break the bond in between each individual ion, which is much, much harder. It's held together a lot stronger. So that sort of stronger the attractive forces between molecules, the less likely that you'll sort of find them in gas phases under normal conditions. And again, if you have any questions, feel free to type them. Even if we sort of move past that, I will be sure to go back and answer your questions if you do have them. So under normal conditions, there are some things that are found as gases, and these are our diatomic molecules. A lot of those ones that we talked about, how they sort of naturally come in that sort of as twos, things like hydrogen gas, nitrogen gas, oxygen gas, fluorine and chlorine gas. Those are all gases under normal conditions. Remember, that's sort of how those elements are found by themselves uncombined. Ozone as well, which is O3, is a gas. And, ozone layer is good in certain parts of atmosphere, not so good in other parts. And then, of course, on our periodic table, group number 8 there, which is our noble gases. These are sometimes referred to as monoatomic gases. Monoatomic, again, meaning that they come as basically one atom. So that's your helium, your neon, your argon, your krypton, your xenon, all your ons there in group number 8. So here's just a periodic table. Again, all the guys kind of in the bubbly area here are where we find, again, normally gases under normal conditions. And this brings up a good time, again, to talk about the difference between two words that we commonly sort of hear and talk about when we talk about gases. And that's the difference between a gas and something that's considered a vapor. So something considered a gas, which typically, again, would get the little G symbol, is a substance that under normal conditions and ordinary temperatures and pressures, so things at like 1 atmosphere and 25 degrees Celsius, these are things that normally are found in the gas phase. And that's different than a vapor. A vapor, which by the way, will also get the little G symbol there. A vapor, though, is something that is the gas form of a substance that under these kind of normal conditions of 25 degrees Celsius in 1 atmosphere, they're normally found, though, in some other states. So they're normally found as a liquid or a gas. A liquid or a solid, but can be converted into a gas relatively easy. So the example that we were just talking about is a very good example of this. H2O, which is water. Under normal conditions, we find it as a liquid. Doesn't take a lot of energy, as you know. You could convert water into a gas simply by heating it. And that's why we typically would call water in the gas phase water vapor. We also call it steam, obviously. We don't usually call it water gas, just seems funny sounding. But water is usually referred to again as water vapor for that reason, because under normal conditions, it's found as a liquid, but it can be sort of relatively easily converted into a gas. So when we talk about gases, there's a couple of aspects of gases that are very important. And the big aspect of gases that are important is pressure. And when we talk about pressure, one way that we measure pressure is through the use of a barometer. And as you'll see on the next slide, basically a barometer is or a traditional barometer, as you'll see on the picture on the next slide. It's basically this big sort of container that usually contained mercury, and they would put sort of a glass tube in it. And as sort of the atmospheric pressure, a much better picture coming up. So you usually have this kind of pool of mercury, have this glass tube, and as atmospheric pressure would sort of come down on that mercury, the mercury would rise there in the tube, and you basically could measure, how high the mercury was in that particular tube. And when we talk about units of pressure, and by the way, the barometer was invented there by a guy named Torricelli, and standard sort of units of pressure is that atmosphere. So that's one that we come across a lot. So an ATM is a unit of pressure that we see a lot. Also, another couple units is a TORR, which is a torr, named after this guy right here, invented the barometer, and MMHG. So MMHG stands for millimeters of mercury. So that's millimeters of mercury. And that's because in a barometer, there usually is, on a traditional one, like a ruler, and you basically take a reading on it in millimeters, for example. Sometimes you can take it in inches, sometimes centimeters, but a very common sort of measurement that you would sort of like read off of a ruler is in millimeters, and that's what the MMHG stands for. Again, millimeters of mercury, which is, again, a very common unit of pressure. Now, a relationship between atmospheres and millimeters of mercury are shown there. 1 atmosphere is equal to 760 millimeters of mercury, and that also equals 760 torr. That means that 760 number is an important number. It allows you to do some conversions. So if you have an atmosphere and you want either millimeters of mercury or torr, you're going to use the conversion like so, 760 on top. Again, this could be torr. This also could be millimeters of mercury, which they are equal the same thing. And that would obviously give you torr or millimeters of mercury. And vice versa, if you were starting with torr or millimeters of mercury, which is essentially the same number since it's a 1-to-1 relationship, you would want to divide by 760 to get into atmospheres. So 760, really important number to remember. It again is your conversion factor to go between millimeters of mercury and torr, and atmospheres, which are the 3 sort of common units of pressure that you'll come across. There are definitely other units of pressure we don't use very much here in chemistry. I would say these 3 here, the atmospheres, the millimeters of mercury, and the torr are the very common sort of units. Other units of pressure are a bar, which is about equal to 1.01 atmospheres, a pascal or a kilopascal are also very common units of pressure. PSI, right, pounds per square inch, is another common unit of pressure. But again, in chemistry, probably most of the time, you're going to be coming across sort of these 3 units here. And again, this relationship as well, sometimes people overlook. It is a 1-to-1 relationship between a torr and a millimeter of mercury. which means that's a simple conversion, really. If you have 785 torr, it's basically the same thing as 785 millimeters of mercury. So it's the one-to-one relationship between them. Any questions on that? So definitely those three units you need to know. Again, you need to know how to convert between them. Again, 760 is that sort of conversion factor. And here's a much prettier picture, basically, of a barometer. And like I said, for the most part, they've taken them out of school labs and stuff like that because they do contain mercury. Kind of replace them with, I think they're more alcohol sort of based barometers now. This idea with the mercury rising sort of saying that you hear. And again, on a lot of these, there was sort of like a ruler here where you would measure it. And again, you can measure it basically in millimeters. And, you know, that's how we get that millimeters of a mercury unit. And again, torr basically named after the guy who invented it. So we're going to then talk now about several different gas laws. And when we talk about gases, there's really sort of three variables that we deal with. And the three sort of variables that we deal with in gases is P, which is pressure, V, which is volume, and T, which is temperature. So in some of these gas laws, we kind of look at, a lot of them, we look at two of these sort of variables and sort of keep the third one constant. In other gas laws, we actually sometimes look at all three of these things together. But a lot of them, you know, we take two and sort of keep something constant when we look at them. So the first sort of gas law we're going to talk about deals with the pressure-volume relationship. So it's the pressure and volume relationship. And in Boyle's Law, we keep temperature constant. So we're keeping temperature constant here. And basically, Boyle's Law says that a volume of fixed gas at a constant temperature is inversely proportional to the gas pressure. So we get this relationship here. Oops, come back. We get this relationship here. P1 V1 equals P2 V2. This again is what's considered Boyle's Law. And when we look at it here, these P is pressure. This is sort of before, kind of a before and after type of deal. So P here is pressure. And in terms of the units, can be any units, as long as they're the same. So what that means is if P1 is atmospheres, when you do the calculation, P2 should be atmospheres as well. And again, if P1 was torr, P2 should be torr, and so forth. V here is volume. And volume also can be any unit you like, any type of volume unit you like. Usually that's milliliters or liters in most cases. Same sort of rule here. Again, if V1 is milliliters, then V2 should be milliliters. If V2, for example, is liters, V1 should be liters as well. And this is basically at constant temperature. So we're holding this at constant temperature. And in those conditions, what we see in terms of the relationship is basically as one goes up, the other goes down. So as the pressure increases, the volume will decrease, and vice versa. If the pressure goes down, the volume goes up in this sort of relationship. And it makes sense if you sort of think about gases. What really causes sort of the pressure that we associate with gases, right, are these gas molecules. Because they are completely broken apart from each other, they're flying around. So as they're flying around, you have collisions that are occurring between gas molecules and the container. The increase in the amount of collisions increases the pressure that we associate with gases. So for example, A good way to sort of think about this is sort of like what we were talking about with Le Chatelier's principle. When we talk about sort of the volume here, if it's a small volume, that means these gas molecules that are flying around in there have a very small area to fly. And as they fly around, that means that they're going to hit the container more often, they'll collide with each other more often, and all that's going to increase the rate of collisions. And as the rate of collisions increase, the pressure should start to go up as well. So basically, the rate of collisions here will increase, and thus the pressure will also increase. And that's different than, again, if we sort of increase the volume here, their same sort of three gas molecules. As you can see, they have a little bit more room to sort of spread out in that larger volume. Because they have more room to spread out in that larger volume, it's going to take longer for them to, for example, collide with the container, and a little bit longer for everything to sort of hit each other as they're flying around, because they do have more space. And that means what we'll typically see here is the rate of collisions will start to decrease. And as they decrease, that's going to result in a decrease in pressure as well. So again, the easier way to remember it is larger volume, more area, longer time for collisions, lower pressure. So again, this is what it means about that inverse relationship. One goes up, one goes down. And that's what we see here. This is a typical sort of Boyles Law graph. And what we see at the smaller volume area, we see that the pressure is relatively high. Thus, if we sort of increase the volume, giving everybody a little bit more room to fly around with before collisions occur, we do start to see a decrease in that pressure. And that's typically what we see here in our Boyles Law arrangement. So why don't you give one a try here? So take a minute or so, a couple minutes, and give this one a go. An inflated balloon has a volume of 0.55 liters at sea level, 1 atmosphere, goes to 6.5 kilometers. Pressure is 0.4. If we keep the temperature constant, what is the final volume of the balloon? So take a minute or so to give that a go through. Okay, so when we're dealing with gas laws or sort of gas problems, a lot of times it's a really good idea to sort of pull out the information from the problem and sort of label what it is. So, for example, If you take 0.55 liters, that's a volume. 1 atmosphere, that is a pressure. 6.5 kilometers is actually useless information in this problem. The pressure here is 0.4 atmospheres. And we're looking for another volume. So just by pulling out sort of those variables from the actual problem and label them, it should usually point you in the right direction. You see you have a couple of pressures, you got a couple of volumes. So again, it should head you down to Boyle's Law. Obviously, at this point, we only have one gas law to deal with, but when we do have a lot more by the time we're done with this chapter, again, you're able to sort of a lot of times visualize those things. So if we do take our stuff and label it, we do want to watch units here. So in terms of units, and again, in terms of notation, there's really no rule per se, but usually when we go through the problem, the first sort of numbers become our ones, the second set becomes our twos. And in reality, it would not matter if you kind of technically math-wise swap those guys around as ones and twos. The only thing that would matter is if you sort of mixed information. So what I mean by that is in this particular problem, 1 atmosphere goes with the 0.55 liters. So you want to always keep those sort of numbers together, no matter if you call them all ones or call them twos. Again, math-wise, it would be the same. So here we're going to rearrange really and solve for V2. So basically, when we go to the other side, we're going to divide it out, and that would give us V2 equals P1 V1 over P2. Essentially, when we go across an equal signs in all these gas laws, things end up in the opposite location. So although they're not really sort of written as a fraction, these guys are on top. So if you're going to move anybody to the other side, they would end up on the bottom. And same thing over here, they would end up on the bottom, just like what we just did there. We move the P2 to the other side and it ended up on the bottom. Now, in this case, our volume is in liters. That means that when we do solve for the volume here, it is going to be in liters as well. So if we plug that in, here our atmospheres will cancel each other out. Again, as I mentioned, that's going to leave us liters as the units that are going to be there. And if you do that, we get something like 1.4 liters. Any questions on the calculation? Now, as we've been talking about, understanding sort of the relationship of something like Boyle's Law is important. So again, the relationship with Boyle's Law is as the pressure goes up, the volume goes down, and vice versa. So what we see is in terms of pressure here, we're at 1 atmospheres to 0.4 atmospheres. That means the pressure went down. And what we should see here is the volume goes up, and we do see that, right? It went from 0.55 liters to 1.4 liters. So the volume did go up, sort of based on what we would expect to happen. So if you do understand sort of these relationships between how these variables sort of affect each other, we would, you could kind of check your answer just to make sure. So why is V1 also divided by? It is. It's just a different way of writing it. I assume you're talking about this over here. Yeah. This right here is just kind of like when I did it for PowerPoint, makes it a little hard. This right here is the same thing as up here. They're exactly the same. Technically, this would be times on top and stuff like that. It's just sort of how I think I had to type it in back then. But yeah, they're the same thing as what's there up top. Because technically it's the way that's written, it's V1 over 1 times basically P1 over P2, which if you divide it and multiplied it out, you would end up, with this. That's just more so the PowerPoint, how to put it together. Other questions on this particular one? So the next sort of laws we're going to talk about first here is Charles Law. And Charles Law dealt with the relationship between volume and temperature, keeping pressure constant in this case. And what he dealt with was this relationship, and he showed that at constant pressure, volume would expand when heated, contracted when cooled. And when we talk about sort of its relationship here, we have V1 over T1 equals V2 over T2, which is Charles' law. And I'll come back to this in just a second, just to show you sort of a relationship. And we'll come back to that slide in 1 second here. But one sort of relationship that they saw with sort of Charles' law was this relationship here, that if we took a gas, no matter what gas we got, so we have helium, we got methane, we got water vapor, hydrogen, dinitrogen monoxide. You took all those gases and you basically plotted volume versus temperature. And if you took all those lines for those plots, what we would see is it would always end up at the exact same spot in terms of the temperature, where it would cross the temperature. And it would cross the temperature at this temperature here, minus 273.15 degrees Celsius. And that number might look familiar to you, the 273. That is the number that we use to convert a temperature into Kelvin. And Kelvin did recognize this relationship, and he called this absolute zero, and later renamed as basically the Kelvin temperature scale. And that is because if we take this number and convert it into Kelvin, that would be 273.15, which gives you 0 Kelvin, which is considered absolute zero. So this is important for gas laws, because gases do behave this way, that when we look at something like Charles' law here, we get V1 over T1 equals V2 over T2. The volume here can be any unit. Again, just like what we were talking about in the previous one, they do have to match. So V1 and V2 does have to be the same unit. Now T1 and T2 and pretty much temperature in any gas law that you have does need to be in Kelvin. So you do need to make sure, pretty safe bet, that if you're using a gas law and you got a temperature that you need to use in there, it does need to be in Kelvin. And again, to do that, as we just saw, you don't need the 0.15. You take the temperature in Celsius, you add 273 to it, and that will get you your temperature in Kelvin. Now, this is also for problems where they give you the temperature in Celsius and they ask you for the temperature in Celsius. You still need to convert it to Kelvin. So you need to go from Celsius, convert it to Kelvin, put it into the gas law, and you would solve for Kelvin. And then you need to go from Kelvin back to Celsius and stuff like that. So sometimes people come across questions like that where they're like, they gave me the temperature in Celsius, they want the answer in Celsius. Oh, I don't have to do the conversion. But the answer is yes, you do have to do the conversion. So any gas law, if you have temperature, needs to be in Kelvin, and that's sort of a safe bet. So let's talk about sort of the relationship here between sort of volume and temperature and sort of this constant pressure. So when we talk about this constant pressure and volume and temperature, first off, if I have my volume and my 3 gas molecules here flying around, and if I say increase the temperature, so if I start to heat it and I increase the temperature, what's going to happen to my gas molecules is they are going to start to move around faster. And because they're gaining all that energy, they're going to start to fly around faster. And that's going to increase the rate of collisions, as we would expect to happen. Now, the problem, though, here with sort of Charles' law relationship is we're at constant pressure. That means if nothing happens and we just keep what we got pictured there on the right just the way it is, we increase the temperature, what we would expect to happen is the pressure should start to go up in this case. And that's not really what Charles' law sort of relationship is. So the way it's able to maintain sort of constant pressure is as we increase the temperature and those gas molecules are flying around faster, what happens to the volume is the volume increases. So as the volume increases because of the higher temperature, what that does is it gives those gas molecules, although they are flying around faster, it gives them more area to fly around. And what that ends up doing is keeping the rate of collisions sort of constant. And because it was able to adjust that volume, that rate of collisions remains constant, and the pressure is able to remain constant as well. So the way that in sort of Charles' law relationship that we're able to maintain basically that constant pressure is as the volume increases, it will increase with an increase in temperature. So as we raise the temperature and those gas molecules are flying around faster, we're going to increase the volume to maintain the pressure constant. And vice versa. If the opposite were to happen, if we decrease the temperature, that means that my gas molecules are now moving around slower, which means the rate of collisions would go down. And if the rate of collisions went down, so would the pressure. So what happens in that situation is if we lower the temperature, we're going to decrease the volume. And that's going to, even though they're moving around slower, that's going to keep the collisions rates constant and the pressure constant as well. So the relationship here with Charles' law is as the temperature goes up, so does the volume. And as the temperature goes down, so does the volume as well. And all of that does is because the volume is going up and down, it's able to maintain the rate of collisions and basically keep the pressure constant. Any questions on that? So another relationship that sort of goes with Charles' law, we'll do it here, is a relationship which is known as Guy-Lussac's law. And he looked at the relationship between pressure and temperature, keeping volume constant. And in his relationship, which is very sort of a similar relationship, sort of Charles' law, in his relationship, he found that P1 over T1 equals P2 over T2. And this as well is same deal. Pressure here could be any unit, again, as long as they are the same on both sides. Temperature here does need to be in Kelvin on both sides. And the relationship that sort of that describes Guy-Lussac's law is sort of this opposite one, is if we have our gas molecules here and we increase the temperature, again, our gas molecules are going to be flying around a lot faster when we increase the temperature. It's going to cause more collisions. The difference between this and Charles' law is the volume here is constant, which means the volume is not going to change. And that means we now have guys that are flying around faster. We have a higher rate of collisions. And what we will see is the pressure will go up. And that is sort of the relationship here as the temperature increases. So there's the pressure in this case, and vice versa. If the temperature goes down, the pressure will also go down as well. And that is because same idea, if we have our same container here, again, our volume is not moving. When we decrease the temperature, our gas molecules again are going to be flying around slower. And as they're flying around slower, that means there's going to be less collisions happening. And less collisions is going to get us to a lower pressure sort of situation. So in Guy-Lussac's law, because of that constant volume, it has nowhere to go in terms of its volume. Nothing's going to adjust, and we get this relationship. So again, this is usually called Guy-Lussac's law. The P1 over T1 equals P2 over T2. Basically works the same way as sort of Charles' law. Any questions on that? All right, let's try one here and see how you do. So take a minute or two. In an experiment, 452 milliliters of a gas is using a light bulb. It goes from 22 degrees Celsius to 187. What is the final volume? So take a minute or two and see what you come up with. Okay, so let's take a look here. So again, if you sort of take the same approach here, since now we got a few gas laws to sort of choose from, we have 452, which is a volume. Light is going from 22 degrees Celsius, which is a temperature, to 187 degrees Celsius, also a temperature. Here we are looking for a final volume, and that should sort of scream to you there a little bit there. That just looks very much like Charles' law. So again, we are going to have a few more gas laws as we keep continuing through this. Um, This will sort of point you usually in the right direction if you sort of just pull out the information. Couple of things in this case, we are going to be solving for V2. So again, basically you're going to multiply T2 to the other side, or if you just want to take sort of when you go across the equal sign, it ends up in the opposite location. So that guy should end up on top. And that would get us V1 T2 over T1 equals V2 when we rearrange it. So a couple other important things in terms of our volume here, we're in milliliters, which means technically when we solve for volume, we will be in milliliters. We also do for both of these temperatures and in any gas law, these guys need to be converted to Kelvin. Obviously, before we go into the gas law, doing our 273. So if we do both of those conversions, we do get 295 Kelvin for the 22. And it looks like we get 460 Kelvin there for our 187. At this point, again, the other thing sometimes people mess up on is putting everybody in the right spot. So labeling everything helps you with that. So you don't invert any of the temperatures or anything like that. So putting it into our equation here, we end up with our 460 on top. Again, our Kelvin going to cancel. Going to leave us with milliliters. So again, we're basically taking here our V1 times our T2 divided by our T1. And when we do that, we end up with 705 milliliters as our final volume. Any questions on that calculation there? And again, we could kind of use what we know about Charles' law, which is what we're using here. What we know about Charles' law is as the temperature increases, so should the volume, and vice versa. If the temperature goes down, so should the volume. So let's take a look here. Our temperature went up, and we would expect that our volume goes up as well, which it did. It went from 452 to 705, and we did see sort of the right sort of final answer, if you will, in terms of what we would expect based on Charles' law. Again, that's a good thing to sort of keep in mind. Very common in gas laws, people will always sort of invert numbers sometimes. So they'll use T1 instead of T2 and vice versa and stuff like that. So again, you could kind of look at your answer if you understand these relationships and make sure that it does make sense. Any questions on any part of that calculation there? Okay. So bringing us to sort of the ideal gas law, but before we do that one, we're just going to add one more to our list. And where do I want to put them? So before we get to the ideal gas law, there is another sort of gas law, and it's from our good friend Avogadro. You remember he had a number. He also has a gas law. And Avogadro's gas law is V1 over N1 equals V2 over N2. And this is at constant temperature and pressure. And basically under sort of constant temperature and pressure, the volume of a gas is related to its moles, and that's what the N stands for here. So the N on both sides are moles. And then the V is volume. So we could use Avogadro's law just like any other gas law. If you have two volumes and two moles, you can basically plug and chug into that. And basically what Avogadro's law here says is that as the volume of a gas increases, so does sort of the proportion of the moles. So for example, if we had one sort of aspect of Avogadro's law is if we had, say, this equation here, like that. So if we have this equation, we can look at these numbers like we talked about with stoichiometry, and we could say, hey, there's 2 moles of H2 and 1 mole of O2 gives us 2 moles of H2O. And if we were dealing with sort of this gas under a Avogadros Law conditions, which would be constant temperature and pressure, we could look at those guys and say that there would be 2 liters of H2, gives us 1 liter of O2, gives us 2 liters of H2O. So sort of what Avogadro's law sort of states is the volume is basically related to the moles of gas that are there under constant temperature and pressure conditions. So um, if you were to use sort of Avogadro's law, you would use it like any other gas law, plug and chug sort of into it. And again, it's V1 over N1 equals V2 over N2. Again, volume can be any unit you want on either side as long as they're the same, and N is the moles. So with that Avogadro's law and taking pretty much Avogadro's law, Boyle's law, Charles' law, and putting them all together, that gives us basically the granddaddy of them all there. It is the ideal gas law. And the ideal gas law is PV equals nRT. And PV equals nRT is, again, the ideal gas law. It is also a gas law that is different than pretty much all the other gas laws that we sort of have seen up until this point. Up until this point, a lot of the gas laws have been sort of before and after sort of conditions. So, like we see here with Avogadro's law, there's V1 over N1 equals V2 over N2. Boyle's law, P1 V1 equals P2 V2. Charles V1 over T1 equals V2 over T2. Guy Lusik's P1 over T1 equals P2 over T2. So a lot of before and after conditions. Here with the ideal gas law, there is no before and after. There's basically just one set of conditions. So you got one pressure, you got one volume, you got one temperature. So it's not so much a gas law that's used to sort of describe how something is changing, but it's used to sort of describe what is going on in that particular gas at that moment without changing anything. Now, PV equals nRT is the ideal gas law, and out of all the gas laws, it is the most restrictive in terms of the units that things have to be in. So when you use the ideal gas law, pressure has to be in atmospheres. So if you put a pressure value into PV equals nRT, it does for sure, if you want the right answer, have to be in atmospheres. Volume here has to be in liters when it goes into the ideal gas law. N should be moles unless something's weird. And T does has to be in Kelvin. So again, out of all the gas laws, your ideal gas law there, PV equals nRT, is definitely the most restrictive in terms of those units. Everybody has to be in those units. And the real reason why everybody has to be in those units is for this guy right here, R. R is a constant, and it is the gas constant. And R, as we will see, equals 0.08206. And some people will round this number to 0.0821. And I don't really have a preference. Personally, I use the 0.08206 because that's what they beat into my head, and I can't get it out as much as I try. But that's the number I typically use. But very common nowadays in books and stuff like that. People will round to 0.0821. So you can use either of those numbers. Should be perfectly fine. Should really give you the same answer, pretty close. And the reason really why everybody has to be in those units is the gas constant itself has actually a bunch of units associated with it. So when we look at the gas law, the gas constant here is 0.08206 liters times atmospheres on top, divided by Kelvin times moles on the bottom. So the gas constant has all 4 of those units in it. And that is why when we use the ideal gas law, everybody's got to be in those units for everything to properly cancel out. The good news is, since R is a constant, you always have this number. And you probably will always have these units there with it, which means if you forget what unit somebody needs to be in, when they use the ideal gas law, it tells you right here what everybody's units should be. You could look at the R value and you can basically use those units. So this is the ideal gas law, and it describes an ideal gas. And pretty much in this class, every gas that we deal with will be considered an ideal gas. And a little bit later on in the chapter, we'll talk about what sort of makes something an ideal gas. If you go on to take, what do they call that class there here? 1A perhaps? You'll deal with what are sometimes referred to as real gases, which is some variation on this. But pretty much everything here that we deal with will be considered an ideal gas or under an ideal gas situation. So R you always have does not always appear, or most of the cases will not appear in an actual problem. So they usually will not just straight out go R is this. They assume that you know what the R value is. So if you feel like, hey, I should be using the ideal gas law, but I'm missing R or something like that, they didn't give it to me, they typically will not give it to you because they assume that you know what it is. And a couple of other sort of important relationships is something known as STP. So we'll start with that. So STP stands for, as it says here, standard temperature and pressure. So if somebody says this gas is at STP, they are actually giving you a temperature and a pressure. The temperature at STP is 273 Kelvin, and the pressure is 1 atmosphere. So if you see a problem where they say it is at STP, that is essentially what the temperature and pressure values you should use. And you can use those values in any of those gas laws that we just saw earlier. You can use it in the ideal gas law, PV equals nRT. You could use it in any of those other ones that have pressure and temperature associated with it. But that is exactly what that basically means in terms of values. Now, there is a relationship, which is really what this top one is here, and it is only for STP condition. So if the temperature is 273 and the pressure is 1 atmosphere, then you can use this relationship here, which is 1 mole of any gas that you have will equal 22.414 liters. So this is a conversion sort of factor, which again can only be used at STP conditions, that will sometimes allow you not to have to actually use the ideal gas law. So in some cases, you can kind of avoid using the ideal gas law under STP conditions by using that conversion there, that 1 mole equals 22.414 liters. You can always use the ideal gas law under any conditions. So you can use it under STP conditions, which means you would just stick in those numbers, the 273 and the 1 atmosphere, into the ideal gas law. You can use it under non-ideal conditions when it's not STP conditions. So the ideal gas law you can use anytime you like, STP, non-STP, but this 1 mole equals 22.414 has to be STP conditions. So if your temperature is not 273 and your pressure is not 1 atmosphere, you should not be using that relationship that's boxed there with the 22.414 liters. This is truly how we do get to the value of the gas constant, which is R. If we take the ideal gas law, which is what they did here, and they solve it for R, and they put in all of our conditions here at STP, what we end up getting is our 0.08206 number, and that's again why it has all those units associated with it. So STP means 273 Kelvin, 1 atmosphere for pressure, and only specifically at STP, you could use that relationship of 1 mole is 22.414 liters, which again may allow you not to have to use the ideal gas law. Any questions on that? So why don't you give this a go, see what you come up with, calculate the pressure in atmospheres exerted by 1.82 moles of SF6 with a volume of 5.43 liters and a temperature of 69.5. So take a moment or two and see what you get. All right. So again, here, just like any other gas law or gas problem, let's just pull out the information. So in this particular case, we are looking for a pressure. They did give us moles, which is N, 1.82. They did give us a volume, which is 5.43 liters. They gave us a temperature, which is 69.5 degrees Celsius. So again, here we see we have a pressure, we got a volume, we got moles, we got temperature, we got just one of each of those. Again, not usually given to you. You always have R. So you could sort of see the ideal gas law there from sort of the information that's given to you. In this case, we would be solving for P, which means P would be nRT. We're going to bring them to the other side to the bottom and divided by V in this particular case. So when we look at this stuff, a couple of things we need to maybe take care of. Actually, only one. It looks like it is our temperature that does need to be converted into Kelvin. Our volume's already in liters. I will say it's a very common conversion that she has to do with the ideal gas law is a lot of times you're given the volume in milliliters and you need to convert it to liters. So again, although we don't need to do it in this case, very commonly 1000 milliliters equals a liter is a common conversion that you sometimes will need for the volume. But again, in this case, it's already in liters, so we don't have to worry about it. Other kind of common conversion that you sometimes have to do that you do not need to do in this problem as well is the moles part. So sometimes the molar mass from the periodic table is needed because a lot of times you're given it in grams. So in this case, as I mentioned, everybody's sort of in this right unit except for our temperature, which we will add 273 to it. And again, just to give you the number, if we added the 273, that's 342.5 here. And again, in terms of units, our liters are going to cancel, our Kelvin will cancel, and our moles will cancel, which is good. That's going to leave us just atmospheres left in terms of our unit. Here, I actually did use the 0.0821 in this calculation. We're going to multiply everything on top. And again, this is our N, this is our R, this is our T, and this is our V, right down on the bottom. And when we do that, it looks like we end up with 9.42 atmospheres as our answer there. Any questions on that? So in this case, a lot of the guys were in the correct units, but like I mentioned before, very common in sort of ideal gas law problems. You have grams and you need to go to moles. So again, the molar mass from the periodic table is going to allow you to do that, which we didn't need to do here from the periodic table. And also very common is milliliters to liters is a very common conversion. And again, that 1,000 milliliters equals a liter. It's another very common conversion, along with what we saw here, almost always Celsius to Kelvin. Again, 273 plus temperature in Celsius, right? So, these are three sort of common conversions that are oftentimes used with the ideal gas law, just to get everybody in the right units. And sometimes you have to do all three of those in this conversion. Any questions on that? All right. So continuing with our gas laws, because we don't have enough, there's actually sort of a gas law that relates all three sort of variables together. And how we get there is what we see going through here. If we take the ideal gas law basically and solve for R, which is the constant, that means that this number and this number is the same. So that means we could take this entire thing and put it equal to this entire thing, which is where we get to down here. But in most cases, when you're dealing with a gas, if you don't open up the top, right, gas molecules have nowhere out, right? So usually if you don't open the top or anything like that, which is usually the case, the moles at the beginning and the moles at the end are the same. So this essentially will reduce down to another gas law, which is known as the combined gas law, is what that one is sometimes called on the bottom there. So the combined gas law basically deals with all three variables at once. So as you can see, P1 V1 over T1 equals P2 V2 over T2. Now, in terms of units here, pressure can be any unit. Again, as long as they are the same on both sides. So you can do atmospheres on both sides. It could be torr, you could do millimeters of mercury. Volume as well can be any unit. Again, probably either liters or milliliters, but needs to be the same on both sides. And our temperature here, like every other gas law, does need to be Kelvin though on both sides. So T1 and T2 here does need to be in Kelvin like normal. And this basically allows us to see what happens if we actually change two variables as well. So we change the pressure and the temperature, for example. We can see how the volume changes. We change the pressure and the volume. We can see how the temperature changes. So this is the combined gas law. The nice thing about the combined gas law is you could use it to figure out the other gas laws we talked about. So if you remember, Boyle's law is at constant temperature. So you take out the temperature part and you're left with the top part, which is Boyle's law. Charles' law was at constant pressure. So if you take the pressure out of there, you're left with V1 over T1 equals V2 over T2. And Guy-Lussac's law was at constant volume. So if you take the volumes out of both sides, you're left with P1 T1 equals P2 T2. So you could kind of use the combined gas law to get to your Boyle's law, your Charles' law, your Guy-Lussac's law, and so forth. So that's if you're concerned about remembering all the other formulas, You essentially can remember the combined gas law and try to remember, this is at constant temperature and get rid of the temperatures out of there. This is at constant volume, get rid of the volumes, and you'll be able to sort of figure out, all the other sort of gas laws from this one. Any questions on that? Also, I would say this is the one that gives people the hardest time in terms of rearranging the equation and solving for things correctly. Things always end up sort of in the wrong location. So why don't we try our hand at rearranging and so forth. So we have oxygen gas at 27 degrees with a volume of 9.55 liters and a pressure of 297 atmospheres, 2.97. The pressure goes to 8.25 and it goes to 125 degrees Celsius. What is the new volume? So take a minute or two and give it a go. All right, so let's take a look at this one here. So again, if we go just pulling the information out, we have a temperature that's 27 degrees Celsius. We have a volume that is 9.55 liters, and we have a pressure that is 2.97 atmospheres. We have another pressure of 8.25 atmospheres. We have another temperature 125 degrees Celsius. And we are looking for a volume. So again, it should really point you to our P1 V1 over T1 equals P2 V2 T2. We are in this case going to be solving for V2. That means that the T2 will go across to the top, the P2 will go to the bottom. And again, what we will end up with is P1 V1 times T2 divided by T1 P2, and that's going to equal our V2. So again, you want to make sure that you know how to properly sort of rearrange these things so that you get everybody in the right location. You don't have the sort of wrong guy on the wrong side. In terms of units, our pressures are okay. They're both in atmospheres. And in terms of volume, it's in liters, which means when we solve for volume, it'll be in liters. Like usual, our temperature does need to be converted to Kelvin. And it looks like if you do those conversions there, you got 300 Kelvin for the first temperature and 395 for the second. Again, here's why it's important to make sure you know how to rearrange it so that you put all the numbers in the right spot. And if you do that, and again, rearranging it, that's going to give us our, like we see sort of above, this is going to be our P1. Excuse me, this is our V1. This is our T2 divided by our T1 and our P2 in this case. Again, properly rearranging in terms of units, we will see that the atmospheres will cancel, the Kelvin will cancel, and that is going to leave us just liters left over, which is good because we are solving for a volume in this case. And it looks like we will end up with 4.56 liters as our final volume. Any questions on that? And we do see sort of a similar relationship, right? The pressure went up, volume went down, and the temperature also increased, which would increase the pressure as well. So all those sort of relationships still sort of apply. Any questions on this particular one here? All right, so that is the combined gas law. Again, could add it to our big list here. So we have Boyles Law, Charles Law, Guy-Ludwig's Law, Avogadros Law, ideal gas law, and the combined gas law here. So far, we've got a couple more things to talk about in terms of gases, then we'll be pretty close to the end of this chapter. But I think for today, this is a good stopping place since we're nearing the end, and we will stop lecturing there. Couple reminders. On Wednesday is our next exam, so that will be some chapters 3, 4, and 5, I believe. So that should be nomenclature, that should be Lewis structures and geometry and polarity and all that kind of stuff, and that should be stoichiometry, limiting reagents, percent yield. Any questions on that stuff there? Like usual, you will not be given any type of polyatomic ions. You won't be given the geometries. You will need to know all those things. We're not going to have a lecture on Wednesday, much like what we did the other time. So it will start probably somewhere around our lecture time, maybe 7-ish, maybe a little earlier if you want to get a kind of an earlier jump on it. So it'll probably be open about 7 for again a window of time like it was for the first exam. Remember that window of time is not to start it. So again, when it says it's the unavailable part, or when it stops being available, say at whatever time it was, say 10 o'clock, for example, that means at 10 o'clock, it will cut you off. Yeah. So don't start right before. Make sure you start an appropriate amount of time, obviously, to get as the appropriate time that you should have for the exam. But remember that cutoff time is a hard cutoff, so you can't just start like 2 minutes before the ending because it will not let you finish. It will just give you like 2 minutes before if you started like 2 minutes before the ending time. And I will not open the exam for you. Yes, again, so make sure you start it with the appropriate time. So if you start too late, you're out of luck. I will not open it for you again. So make sure that you plan appropriately to give yourself the maximum time. You also will obviously, like last time, need to work out stuff on paper for sure this time, including things like Lewis structures and stuff like that. So make sure that that is all labeled correctly. It is all neat. Also, when you upload it, make sure that the picture that you take or whatever it is legible, not too much shadowing, like it's really dark, you can't see anything. Yeah. So make sure that you can see it. Take a look at it before you upload it to make sure you do that. Remember that the answer that you submit online needs to match that the answer that you have on the paper. And if they do not match, I'm not looking at your work. Yes. And, you know, you'll just get a 0 for that question. So they better match. Remember as well that there are different versions, so don't have the right answer on the wrong version or anything dumb like that as well. Um, you do need to make sure you answer everything online. Again, otherwise, if you don't answer it online, your work will not be looked at for those questions either. So, they has to match in both places, or we just go with the answer that you gave online and you don't have work and you lose points. So make sure all that is shown correctly. You also need to upload your work again in a timely fashion after you submit your exam. So it shouldn't be hours or hours later. It should be pretty immediate after you're done with the exam. You should be able to upload your work. So there shouldn't be hours of delay or anything weird like that. You have an amount of time to do that. Make sure you do it in the appropriate time as well. Yes, just like the first exam, it will clearly say on each question, hey, you need to show work for it in red, or in blue, it will say you don't have to show work for it. So, yeah, just like the first one and the quiz, too, I think it will clearly say which questions you need to show work for sure. Yeah. And remember that all that work should show any type of units set up, obviously, the same answer as we've been talking about that you got online and everything like that. So again, like I said, there won't be a live lecture on Wednesday. That should free up that time for you to sort of take the exam and all that good stuff. We will then continue live lecturing back on a week from today, I guess, on next Monday. And we'll continue through this chapter, maybe get into chapter 8-ish, I think, at that point, and stuff like that. I think we're actually on schedule, so that's good in terms of the syllabus, I think, and the chapters and stuff like that. I did move the online homework, so I think it's now due this coming Friday. So if you haven't finished, make sure you also finish that stuff as well. Any other questions on anything? Okay, so good luck on your exam on Wednesday and all that good stuff. I think I saw an email from Dr. Tyler about lab and stuff today. So if you didn't check Canvas or the announcements, make sure you do, just to make sure you catch her at the time she's going to be there. All right. Other than that, have a good week, I guess. If you need any questions, I also did put some exam review and some stuff up online as well. So make sure you take a look at that. Have a good week. Have a good day. And I will see you live again next week.